Welcome back, everybody. In this video, I'm going to state the axiom of completeness for the real numbers and give some examples as well as maybe prove a related theorem and give some more examples. So we'll see a bunch of examples here of computing suprema and infima. But let's start with the namesake here, axiom of completeness. So this is going to be an axiom which from our point of view, right, is going to mean we're not going to prove it. Okay, we're going to take this as a statement which we assume is true. So an axiom of completeness here. So the axiom of completeness is going to say that every nonempty, upper bounded subset of the reals. Okay, so I start with some nonempty set, and it has an upper bound. And in the video on bounds, we asked whether or not if you had an upper bound that meant that necessarily you had a least upper bound or a supremum. And the axiom of completeness is if you have any upper bounded subset, which is non-empty, then it does have a supremum. Okay, so that's the statement. This has a supremum. So this is the existence part, right? We showed in the video on bounds that suprema are unique for a set. So if it's upper bounded, then there's at most one supremum. And this says that there, as long as it is upper bounded, there is at least one supremum. So in fact, we know there will be exactly one supremum. Okay, so we'll take an example set. So let's say I look at the set that has all numbers of the following form. This is going to look a little bit weird at first. So I'm going to take some sum from 1 to n, and I'll just tell you right now, n is some positive integer. Okay, well, I need to say what I'm adding up. And they're going to be fractions that look like 9 divided by 10 to the k. So what is this really? Well, you see 9 over 10 to the k. Well, 10 to the k is either 10 or 100 or 1,000 or 10,000, etc. And if I do 9 over that, then I'm looking at 9 tenths or 9 hundredths or 9 thousandths or whatever. And when I start adding all those up, well, let's see. Let's say I just made n equal to 1. I would get 0.9, okay, 9 tenths. If I make n equal to 2, then I would get 9 tenths plus 9 hundredths, which is 0.99. Or if I made n equal to 3, then I'd get 9 tenths plus 9 hundredths plus 9 thousandths, which would be 0.999. So you see what we're getting here, right? There's a weird way to write it, but that's math for you. Okay, so I'm just looking at all of these decimals that have just 9s in the expansion. Okay, so this is some set, and I would like to know, is it bounded? Right? Certainly non-empty, but is it bounded? And of course it is. You can see by putting these 9s on the end, I'm never getting as big as, say, I don't know, 5, right? It's definitely not getting any bigger than 5. So this is upper bounded. And so by the axiom of completeness, it must have a least upper bound, right? It must have a supremum. Okay, so now it'll give a name to the set. How about we'll call it A? So by the axiom of completeness, which how about we abbreviate that, AOC. Okay, by AOC, A has a supremum. In fact, we can even find the supremum. It takes a little bit of work, right? But you might see, okay, well, all of these are not only less than 3, but they're less than 1. And in fact, I can get as close as I want to 1, but I never actually get to 1. Okay, so 1 is not in this set. However, it is an upper bound, and you can't get anything smaller. Okay, so again, there's a little bit of work to prove that. Okay, I'm not going to go through that at this moment, but that'll be true. In fact, the supremum of A is 1. Okay, so 1 is the least upper bound. All right, let's do another example. I'm going to call this again a non-example. So let's look at the interval that goes from 0 to the square root of 2. But I only want to consider numbers in this interval that are rational. Okay, so I only want the fractions in here. And just because this is long notation, I'm going to shorten this up and write a little subscript here, a Q, that just tells me only look at the elements in this interval that are in Q. Okay, this set does have a supremum. Okay, the axiom of completeness says if you have a non-empty, this is definitely non-empty, upper bounded, well, yeah, nothing in here is bigger than the square root of 2, right? Then it has a supremum. So this has the supremum, and in fact, the supremum is the square root of 2. Okay, but let's go into an imaginary world where we only are looking at upper bounds that are rational numbers. And so when I ask for the supremum, I only want a supremum that is a rational number. Okay, so that's not the world we're living in, but it's a world I could ask to live in. Okay, so is there what we might call a rational supremum? And it turns out the answer is no. Okay, so there is no rational supremum. Okay, which means that the axiom of completeness really does depend on this of R, right? That we're working inside the real numbers. If we were just working inside the rational numbers, we may have sets that are upper bounded, non-empty, but don't have supremum. Okay, now why is this actually true? Well, we're a little bit away from, I mean, we're not there yet where we can prove this, but in a future video, we're actually going to prove something called the density of the rationals in the reals. And what that would tell us is that between any two real numbers, so if I have, say, a real number A and a real number B, the density says that in between those, there must be some element, x, which is bigger than A, less than B, but is a rational number, right? So you can find a rational between any two real numbers. Okay, so we'll prove that in a future video. So what we could do here then is say, well, what if, so if, say, little s is a rational supremum, then, well, we know that since the square root of 2 is a supremum, right? It is the least upper bound of all of the bounds, then this rational supremum certainly can't be any smaller than the square root of 2. All right? So the square root of 2 has to be smaller than this s. Okay, but now I have two real numbers, and by this result that we haven't proved yet, I know that there is some rational number in between them. So there's some x which lies in the rationals, which is bigger than the square root of 2, but which is less than s. But if x is bigger than the square root of 2, then x is an upper bound for our set. Right? So x is an upper bound for this set of rational elements in the interval 0 to the square root of 2. But it's less than the supremum, right? It's a rational number less than the least upper bound. Okay, this is a contradiction, right? So, and x is less than s, a contradiction. Okay, so this shows that there is no rational supremum. All right, now, everything I just said for suprema should hold for infima, but the axiom of completeness doesn't say anything about infima. So what we're going to do is use the axiom of completeness, a statement fully about suprema, to prove something about infima. And this is a very common thing to do in math, where you have some sort of dual notions, where you only have to assume something about one of them, and then you can use the duality to port that information over to that dual notion. Okay, so let's write down this as a theorem. Okay, and so the theorem is going to be, well, the axiom of completeness is that suprema exist, so the dual statement will be that infima exist. Okay, so as a statement, every nonempty lower bounded subset of the real numbers has an infimum. Okay. So the way we're going to prove this is by taking this nonempty lower bounded subset, and we are going to convert it into another subset which is upper bounded and nonempty. And so we'll know it has a supremum. And then we'll convert that supremum back into an infimum. All right. Now, let's start the proof. So since this theorem doesn't have a particular subset in mind, let's start with one. So let's let A be some subset. Okay, and let's say that it is non-empty and lower bounded. Okay. And in fact, if it's lower bounded, there is some lower bound. So let's say it's lower bounded by, say, the number L. Okay, so this is some real number. Okay, so I want to define a new set, which is going to be upper bounded. And I'm going to call this set negative A. Okay, and the elements of this set are just the negations of every element in A. So I take every element of A, and I just put a negative sign in front of it. Okay, and this gives me a set which I'll call negative A. Okay, this set is obviously non-empty because A was non-empty. Okay, so this is a non-empty subset of the real numbers. Okay, well, what if I take some element in A? We know that L is a lower bound. Well, that means that L is less than or equal to little a. But if I multiply then this by negative 1, then I get that negative A is less than or equal to negative L. And so this shows me, well, I know that everything in negative A looks like the negative of some little a. And this shows that every one of those negative little a's is bounded from above by negative L. So it follows that negative A is upper bounded by negative L. Okay, everything in negative A is less than or equal to negative L. Okay, so I now have a non-empty subset of the reals, which is upper bounded. And so by the axiom of completeness, I know that negative A has a supremum. Okay, and at this point, it's probably good to introduce some notation for the supremum, since we're going to want to use this number here. And because we already know by the axiom of completeness that the supremum is unique, I can really talk about the supremum of negative A. So I'm going to denote this by SUP of negative A. So SUP for supremum. Okay, so I have this supremum, the least upper bound for the set negative A. So again, I have this element little a and we now know that if I take negative a, that this has to be less than or equal to the least upper bound for the set negative a, right? So it's less than or equal to the supremum of negative a. And of course, we already know that the supremum is the least of the upper bounds, so it has to be less than or equal to any other upper bound, including negative L. Okay, so now we unravel this, right? We go back. Okay, we went from the infimum world over to the supremum world, right, by taking a negative. Now we want to get back to the infimum world. So I multiply again by -1. So this implies when I multiply by -1, everything's going to turn around. L is less than or equal to the supremum, the negative rather, of the supremum of negative a is less than or equal to a. So what does this tell us? This tells us that I have some number which is less than, or rather is greater than or equal to this lower bound. And this lower bound was any lower bound. Also, it tells me that this number is less than or equal to any little a in the set A. So I have two statements here, right? So the first, well, actually, let me start on the right. The first is that because negative of the supremum of negative a is less than or equal to a, little a for any a, I know this means that the negative of the supremum of negative a is a lower bound for a. Okay, it's less than or equal to every element in the set A. On the other hand, I have that this negative of the supremum of negative a is greater than or equal to, well, this lower bound L, but this lower bound L could have been any lower bound. So in fact, negative of the supremum of negative a is at least as big as every lower bound for A. Well, that's what it means to be an infimum. You are a lower bound and you're at least as big as all the other lower bounds. All right, so therefore, negative the supremum of negative A is an infimum, right? In fact, the infimum, because we already showed that, right, that it's unique, so is the infimum of A. Okay, and as long as we introduce this notation, SUP for the supremum, we might as well introduce notation for the infimum, and that'll be INF of A. Okay, so i.e., the infimum of A is equal to the negative of the supremum of negative A. Okay, so that's a nice sort of duality there between the infimum and the supremum of a set. Okay, so now we have some notation, and maybe we will do an example, all right? Or two, or whatever. So let's say I take a set A, different A from up above, and it's going to contain elements of this form. I'm going to start with an alternator. So an alternator for me is always -1 to some integer power. So I start with an alternator, and then I'm going to add a harmonic number. That's just 1 over a natural number. Okay, so here n is going to be some natural number or positive integer. So I would like to know, first, do suprema and infima exist? And if they do, what are they? So it's a little hard for me, when just given this format, to figure out what the answer is. So what I might do is try to break it down a little bit, or maybe even write out some examples. In fact, why don't we do that here, right? Let's start with doing a couple examples, right? So when n is equal to 1, I get negative 1 to the 1 plus 1 over 1. Okay, negative 1 to the 1 is negative 1, plus 1 over 1 is 0. Okay, fine. N equals 2. Negative 1 squared plus 1 over 2. Well, negative 1 squared is 1, plus a half is going to be 1.5 or 3 halves. Okay. What about n equals 3? Well, I get negative 1 cubed plus 1 over 3. That's going to be negative 1 plus a third. So that's negative 2/3. Okay. Yeah, it's like not like helping me so much. Maybe I'll do one more, see if this is helping. Negative 1 to the 4th plus a 4th. So that's 1 plus a 4th. That's 5 over 4. And then all of a sudden something dawns on me. Wait a second. Like half of these, you're getting a negative 1, right? When it's an odd power. And half of them, you're getting a positive 1. That's when it's an even power. And then the rest of it, well, it's just getting smaller and smaller and smaller. So it's like there's kind of two parts to this, right? So I have a negative 1 to an odd power, right? So if I have n odd, then I'm just getting negative 1 plus, well, whatever 1 over n is. And then when n is even, I'm getting a positive 1, but again, plus, right, 1 over n. So there's like two sequences really kind of working together here. So maybe I analyze them separately. Well, what is happening as n is getting very, very big? Well, 1 over n is getting very, very small. So this is basically taking negative 1 and you're adding numbers that are getting closer to 0. So what can I say about 1 over n? Well, let's see. Let's try this. 1 over n, I know what's the biggest it can possibly be. That's when n is equal to 1. So when n is equal to 1, I get 1 over 1. So 1 over n is less than or equal to 1. And what's the smallest it can be? Well, as n gets bigger, this gets closer to 0. It'll never equal 0, but I get there. So if I now add negative 1, I get 0 less than, add negative 1 to everything. So let's add negative 1. Negative 1 is less than negative 1 plus 1 over n is less than or equal to negative 1 plus 1, which is 0. So when n is equal to 1, I actually get 0 in this case. And that's as big as it's going to get. And then as n gets big, I just get closer and closer to negative 1. All right, so maybe I draw a little picture. Might help me out a little bit here. So I know that at some point I get a 0, and then it's negative 1 plus a little something. So it's never actually equaling negative 1, but it's getting very, very close to it. All right, so I'm getting stuff. Now, I don't actually get all of these points, right? I'm just getting some of them between 0 and negative 1, but for the purposes of infimum and supremum, I don't care about the difference. Okay, now what's happening in the n even case? Well, when n is even, I still have 0 is less than 1 over n. It's not actually going to be less than or equal to 1 just because it can't equal 1 anymore, right? The biggest it can actually get is when n is 2, you get a half. So this will be less than or equal to a half. And then I add 1 to everything. Right? So I'll add 1, and I get 1 is less than 1 plus 1 over n is less than or equal to 1 plus a half, which is 3 halves. So the biggest it's going to get, right, the biggest it'll be is 3 halves, right, which we actually saw here when n was equal to 2. So we can put that into the picture. So it's actually equal, so I'll use a little square bracket at 3 halves. And then as n gets bigger, this thing gets smaller and smaller, but never goes below 1. All right, so let's put a 1 in here. And so again, we get stuff, and it actually does hit the endpoint. Okay, so that's what our set A looks like, and now this should be pretty easy to work out what the supremum and the infimum are. Right? So when I'm looking for the supremum, I'm looking first for upper bounds. Okay, and you might say, well, it's broken up into two pieces. Like, do you get two upper bounds? No, a set only has one upper bound, right? It has to be bigger than everything in the set, right? So over here I could have a 10, right? That would be an upper bound. But the smallest of the upper bounds is right on the top here. That's 3/2. Okay, so this is your supremum of A. Okay, so the supremum of A is equal to 3/2. Okay, now what about the infimum? Well, I work now for the lower bound. I go all the way over to the left, and there's that -1 on the end. Now, I never actually get -1, but that's okay, because it just has to be a lower bound, and it has to be the greatest of all the lower bounds. And I can keep getting closer and closer to -1, so I never have to worry about missing something out if I use -1. So the infimum of the set A is going to equal -1. Okay, so there's a nice example. Yeah, this is probably enough. 25 minutes, whatever, 26 minutes. That's good for one video. But you might try playing around. You start messing with examples like this. Maybe make it -1 over n, or -1 to the n over n, and then add 1 or something, right? So you can mess around with these things, and you'll get lots of good examples that way. All right, we will see you next time when we write down some consequences of the axiom of completeness.